So in this lesson, I'm going to be talking about acid-base titrations, and what you'll actually realize is though I'm adding a new concept, this concept of a titration, it's actually material that we've already covered when we worked with acid and base dissociations, buffers, and the common ion effect. So just a quick couple of definitions. A titration is the process of reacting a solution of unknown concentration with one of known concentration. And so you'll get a little bit of practice with that in the problems for the worksheet in this lesson, but then also with a full-blown lab in which you determine the concentration of a base given the concentration of an acid or vice versa. The next concept is the equivalence point. Now the equivalence point is the point at which there are equal amounts of acid and base. And specifically when we say equal amounts of acid or base, we're saying that you have equal numbers of moles of your acid and your base. And so equal numbers of acid and base with regards to moles, that brings up the equation of Ma times Va equals Mb times Vb. And this should look is identical to the dilution problems we worked on, except now we're dealing with acids and bases. Notice the only new thing I added is you multiply the molarity of the acid times the volume of the acid times the number of hydrogen ions. So if you had 2, like your H2SO4, you would put a 2 for that value. And then that's equal to the molarity of the base times the volume of the base times the number of hydroxide ions. And so the point of that is to make sure that once you're at your equivalence point, you know that you have the same number of moles of acid and base, and that allows you to do some calculations. So with this example problem, it tells you you have a 0.150 molar solution of NaOH, and it was used to titrate a 200 milliliter solution that's 0.150 molar of H2SO4. And so I know my molarity of my acid, my molarity of my base, and I know the volume of my acid, and what I'm trying to calculate is the volume of my base. And so for this specific problem, I know since I'm at my equivalence point that I'm going to have equal numbers of moles of my acid and my base. And so I just plug in my values, the molarity of my acid times the volume of my acid times 2 because it's H2SO4, and then I'm going to set that equal to 0.150 times the volume times 1 since the base is NaOH. And so the volume I get for my base is 400 milliliters. So that's the equivalence point, knowing that your number of moles of acid and base are going to be the same. Now that excludes when you have more acid or you have more base, and so that's what we're going to get to when we're talking about titrations in just 1 second. Your end point, when we actually work with titration in lab, your end point is the point at which your titration is complete, and you know it's complete because you have a color change. And so by the point you've hit your end point, you've actually passed your equivalence point. So you have a little bit more acid or you have a little bit more base than you have at your equivalence point. So if you hit your end point, that's how you know in the lab you're done. You've actually kind of passed, just slightly past your equivalence point. And so we'll also see that in the lab. The last concept is your titration curve. Now your titration curve is a graph of your pH, so your pH goes on your y-axis, versus the volume of your titrant, which in a lot of cases tends to be your base. And so what we're going to do right now is we're going to look at examples of titration curves in order to understand titration just a little bit better. So here I show a titration of a strong acid with a strong base. So for example, hydrochloric acid and sodium hydroxide would be a great example. So at the very beginning, right at my x-intercept, I have 0 mils of NaOH, and so as you notice, my pH is very low because what I have at that moment is just all hydrochloric acid, so my pH should be low. As I move along to the right on the x-axis, I'm adding NaOH, so as expected, the concentration of my pH of my hydrochloric acid is going to decrease, which means my pH is going to increase. So I have more and more NaOH, which means I have less and less HCl. And then I hit this point at which the pH suddenly jumps up extremely quickly. And the reason why that happens is right before that happens, I've officially run out of hydrochloric acid to react with NaOH. And so what I have is actually just NaOH, is the OH minus in water. Okay, because as you notice, when your pH equals 7 right there, you don't have any acid or any base. They've completely reacted. And so once I go past that equivalence point where they're equal, and by the way, notice how significantly it jumped up to reach your equivalence point. Once I've passed that point, I only have base left over. And so I'm just having OH in that solution. So the pH is going to continue to spike up until it kind of plateaus up at the top once you get to around 70 to 80 milliliters of NaOH. So this is a titration curve for a strong acid and with a strong base. All right, and what we're going to look at now are practice problems in which we can actually use these in order to determine what exactly is the pH before I have equal amounts of hydroxide and hydrogen ions, what's the pH after that point, and then also what's the pH right when I have equal amounts. And notice at the equivalence point for a strong acid and strong base titration, it's actually 7. The pH is 7, meaning it's perfectly neutral. And you guys should actually understand that because the salt that's present after adding after adding HCl and NaOH. All right, so in this problem, this is going to be a strong acid, strong base problem. Notice that you're adding 24.9 milliliters of nitric acid to 25 milliliters of potassium hydroxide. And so what we're going to do is we're just going to see, all right, do I end up with OH left over? Do I end up with H plus left over? Because these are strong acids and bases. The only problem is because I'm adding 2 different volumes and with certain concentrations, the fact that you're adding the volumes together means that you have to find the new concentrations after you add the 2 solutions together. And so the way that you actually do this is you're going to say, for example, for nitric acid, you're going to say, all right, I have 0.100 molar of my nitric acid. I don't know how many moles that is exactly, but I do know that that's 0.0249 liters. And so what I can do is I can say, all right, well then that's going to be 0.00249 moles. And I'm going to divide that by the total volume of my acid and my base, so 24.9 plus 25.0 converted into liters, and that's going to be 0.0499 liters. Okay, and so what I get for my concentration of nitric acid is 0.0499 molar. Okay, and I'm actually just going to say this is H plus because remember it dissociates completely, so I can actually ignore the nitrate. All right, the next one I'm going to do is for potassium hydroxide, so 0.100 molar equals X over its volume, which was 0.0250 liters. And so that ends up giving me 0.00250 moles divided by the total volume, which is 0.0499 liters. And so what you end up getting here is 0.0501 molar of OH minus. And so what we're going to do now is we're going to say, all right, hydrogen is going to react with hydroxide, and that's going to produce H2O. Okay, I'm going to create a nice chart just to help me to be able to see this. I know I start with 0.0499 of my hydrogen ions. I start with 0.0501 of my base. So all of my acid's going to react because I have less of it, which means I'm going to have base left over. So this is 0, and this ends up being 0.0002 molar. And that's all I'm left over with because, yeah, I do end up with some water, but water is neutral. And so I can calculate my pOH really easily by just taking the negative log of my concentration of OH. And so what I get for pOH is 3.7 based on sig figs. And therefore my pH, if I subtract that from 14, is going to be 10.3. And that's my answer. All right. For the next problem, I'm obviously going to have more acid than base, but let's see how much exactly it is. So what I want you to do right now is I want you to calculate, just like how we did here, the new concentrations of H plus and OH minus based on these new values. So pause the video and do that. And so what you should get here, H plus and OH minus, that's going to produce water. Okay, I'm going to ice that. Concentration that I got when I did this was I got 0.0500, and the concentration I got for OH is 0.0499, which makes sense because I had more acid than base this time, which means I'm going to end up with acid at the end because I'm going to run out of my base. So this is going to be 0.0001, that's going to be 0. And so what I get for my pH, it's just going to be the negative log of my concentration of 0.0001. And so here I get 4.0, and that's my pH. So notice here I ran out of hydrogen ions, here I ended up running out of OH, and so you just use those concentrations in order to determine the pH of each solution. These are really easy simply because you're just ending up with either H plus or OH minus. So we're going to make it a little bit more tricky once we get to weak acids and weak bases. Now what we're going to work on, now that we've talked about strong acid and strong base titrations, we're going to work with strong acid being added to a weak base or a strong base being added to a weak acid. And so what this titration curve right here shows you is actually a strong base, an AOH, being added to a weak acid. Okay? And so what you should be able to see if you start off right at the beginning of this titration curve, notice it's not quite as flat as the strong acid, strong base titration. Okay? You start off with your weak acid and you're adding your strong base. So yeah, the pH is going to increase quite a bit more drastically than when in the previous problem you were dealing with a strong acid and a strong base. Okay? Notice you're going to have that sudden peak up to your equivalence point, that increase in pH, and then past your equivalence point is going to kind of level off again. So it looks similar, but let's focus on how this is different than a strong acid, strong base titration. Notice that as you're adding OH, if you look at the drawings here, as you're adding OH minus, that actually converts your acetic acid into acetate ions, which we've already learned about at this point. Okay, so it's actually going to be forming a buffer solution, meaning you're having your acetic acid and your acetate ions. Okay, your pH is increasing, and then also look at your equivalence point, which is where your number of moles of acid equal your number of moles of base. Notice your pH is not 8. And if we think about that, when you have equal amounts of acid and base, if you have a weak acid, keep in mind that you're going to have a salt that's left over, and in this case, it's your sodium acetate. Remember that that acetate ion is actually acting as a weak base, which is why your pH is a little bit above 8. Which makes sense. So instead of having like NaCl, which is perfectly neutral as a salt, instead you're going to have sodium acetate, which is slightly basic. So when you're dealing with a weak base, strong acid, or strong acid, weak base, when you're at your equivalence point, your pH is not going to be equal to 7. Then notice once you've passed your equivalence point, the pH is going to be increasing because you're adding OH to a solution that no longer has an acid in it. Alright, so in this problem what I'm dealing with is I'm dealing with acetic acid, which is a weak acid, and then I'm dealing with a strong base. So this isn't going to be quite as obvious as the previous one, but the first thing that I need to do, just like with the other problem with the strong acid and strong base problem, is that I need to figure out what the concentrations are of my acid and my base once they're added together. And so for example, I'm going to take the 0.150 molar of acetic acid, I'm going to multiply it by its volume to get the number of moles, and then I'm going to divide it by the total number, or the total volume that I have. So the 35 plus, for example, 34.5 here. And so what I want you to do right now for A, B, and C, you can decide when to pause it. I'm not going to go over those calculations. I'm just going to share with you the concentrations that I got for each of these. Okay, so I would pause for A, and then you can pause in between to do it for each of the other ones to make sure you're good with those calculations. So for this one, for acetic acid, so HC2H3O2, the concentration that I got once I did that math is I got 0.0755 molar. And then for my base, which is OH minus, I got 0.0745 molar. And so in my mind, I am saying, all right, awesome. I'm going to actually run out of base before I run out of acid. Okay, so the reaction that's going to happen between these two when they're added together is the following. Okay, so that's not new. It shouldn't be. I'm going to ice it. Okay, and so what I'm going to now say is, all right, the concentration for this is that. I'm going to have 0.0745 molar of OH. This isn't a buffer, unfortunately, and so I'm not going to have any of that to start off with. And so all of my hydroxide is going to react because it's a strong base. So I'm going to lose 0.0745 molar from both sides. I'm going to add 0.0745 molar to acetate ion, and I get the following. 0.0010. There. All right. Now it asks me to find the pH. Well, what I have right now is I've got a weak acid and its conjugate weak base. I don't have any OH left over, and so what this should make you think about is the Henderson-Hasselbalch equation. So my pH equals my pKa plus the log of my concentration of my base, which in this case is my acetate ion, and acetic acid. Okay, and so I want you to actually plug and chug that in and figure out what it is. And what you should get, make sure you're able to do this, you get 6.61 for your pH. Okay, pause this to figure out the concentrations of OH and acetic acid for this new problem now that I'm changing the volume to 35 mils instead of just 34.5. And what I get for this one is that my acetic acid concentration is 0.075 molar. Okay, and my concentration of OH is also 0.075 molar. Okay, well, in my mind, I'm thinking, oh, cool, awesome. I have the exact same amount of acid and base, which means I'm not going to be left with any of those left over. Instead, what I'm going to be left with is just the acetate ion. So let's see that actually happen. So H2O, which we ignore, and my acetate ion. I'm going to ice this. Okay, and so I start off, concentration-wise, I start off with 0.075 of that, 0.075 of that, we ignore water, 0 of that, and so negative 0.075, negative 0.075, so this is going to be 0, none of that left over, none of that left over, plus 0.075, and so I end up with 0.075 molar. Well, now here's the issue. I've got this weak base and I've got a certain concentration of it. Well, what I can do is figure out what the pH of that solution would be. Well, what I've got to do though is I've got to treat this as it is, which is a weak base. So I'm going to take this weak base and I'm going to add it to water. Notice in the previous problem I could use my Henderson-Hasselbalch equation because I was left over with some acid. Unfortunately here I'm not. So I can't use my Henderson-Hasselbalch equation. I've got to actually write out the reaction for my base with water. So then I'm going to ice this. Okay. I start off with 0.075 of this. Ignore that. I don't start with any of that, unfortunately. I don't start with any of that. And so I'm going to say minus x. This is a typical weak base problem. So plus x, I'm going to have x here and x here, and so when I solve, it's going to be x squared over 0.075 equals, well, this is a KB problem, so make sure that you take the Ka and convert it to kb by taking 10 to the negative 14th and dividing it by Ka. And what you get is 5.6 times 10 to the negative 10th. And this is actually this actually follows the rule of 100, so that's why I got rid of the minus x. And so when I solve for x, what I end up getting is 6.48 times 10 to the negative 6. And so when I solve for my POH, by taking the negative log of my concentration of OH, what I end up getting is 5.19. Notice the question doesn't ask about POH, it asks about pH, so 14 minus that value, and you get 8.81. Okay, so while for this problem I ended up with still some weak acid left over and some weak base, so I could use my Henderson-Hasselbalch equation. For here, what I have to do, since I take up all of my weak acid, what I'm left with is just my conjugate base, and so then I need to do the weak base formula. Okay? Which leaves the question, all right, well, what if I don't have acid left over? What if I don't have equal amounts of acid and base to create the weak base, but instead I end up with extra OH? So what I want you to do right now is calculate the concentrations for C right here, now that I've changed the volume again. And so what you should get once you do that is that your NaOH concentration, what I get for this one, is 0.0755 molar. What I get for my weak acid, my acetic acid, is I get 0.0745 molar. And so in your mind you should be saying, well, awesome, not only is it not equal amounts, but I'm left over with OH. OH is a strong base, which means I can just figure out how much OH is left over and then just plug that into my POH equation. And so I'm going to end up with 0.001 molar of OH. Plug that into my POH because that's a strong base. I can do that really nice and easily. And for my POH, I get 3.0, and therefore for my pH, I get 11.0, and I'm done. So keep in mind, guys, this problem, what this is showing you is, all right, if you have less strong base than weak acid, you're going to end up with a little bit of weak acid and a little bit of its conjugate base, and you can use the Henderson-Hasselbalch equation. If you have equal amounts, well, you're going to end up with some of this weak base, which means you got to use your weak base formula to figure out the pH. But if you're lucky enough to get plenty of extra strong base, you can just plug that concentration of leftover OH in directly to figure out your POH. All right. So unlike the other problem in which I was adding a strong base to a weak acid, now I'm going to add a strong acid to a weak base. And so in this problem, what I want you to do right now, I want you to pause this video and determine what the concentration of your ammonia and your hydrochloric acid would be once I add them together, because that's something that you need to be able to do. Okay, so NH3, once you do that, the concentration of NH3 equals, I got 0.386 molar, okay, and then for hydrochloric acid, I'm just going to write H plus because it's a strong acid, I get 0.357. So looking at that, I know I'm going to have more weak base left over than acid. I'm going to use up all my acid. So I'm going to allow these to react, plus H plus, and that's going to produce NH4 plus. Okay. And so when I allow these to react, I'm going to ice this, and then I'm going to put the concentration of NH3, which is 0.386, the concentration of H plus, which is 0.357, and then I don't start with any ammonium. I'm going to use up all of the acid, so 0.357 minus 0.357 plus 0.357 here. And so what I end up with here is 0.029 molar, none of that, and then 0.357. And so I've got a weak acid, I've got my weak base, and therefore I can use the Henderson-Hasselbalch equation, since I have both of those, and I can solve. So my base in this case is going to be NH3. My acid in this case is going to be NH4. And so you can actually solve, and when you plug everything in, I got 8.17, so check me on that one. Okay? Now, what if I end up with extra H plus rather than extra weak base? Let's try that one. So I want you to figure out the concentrations of these guys right now that I'm using 50 mils of HCl instead of, now that I'm using 60 mils instead of the 50 mils. And so what you should end up getting for concentration of NH3, you should get 0.360 molar. And for H plus, you should get 0.400 molar. Okay? What you should realize is I'm going to run out of NH3 really quickly, and so I'm going to lose all my NH3, and what I'm going to be left over with is H plus, and I'm specifically going to have 0.040 molar of H plus. Well, the awesome thing is now I can just plug that in. Since this is a strong acid, I don't need to use my ice charts, and I can just plug this in to figure out what my pH is. And so what I get for pH is actually just 1.40, and that's it. What I wanted you to notice, we just talked about weak acids and strong base titration curves, and then also strong acid, strong base titration curves. I wanted you to notice, just really focus on how they look different. So on the bottom you have a strong acid, and so that shows the typical titration curve for a strong acid and a strong base. At the very top, notice the Ka is very small, so you have a very weak acid with a strong base. So let's talk about a couple of differences that you see based on the strength of acid that is reacting with the strong base. The first thing is that the weak acid is going to have a higher initial pH than the strong acid, which makes sense because remember, a strong acid has a very low pH while a weak acid has a higher pH simply because it has fewer hydrogen ions that have dissociated because it's not good at breaking apart. That's what makes it a weak acid. Another thing is that the pH change that you see to reach the equivalence point and beyond, it's less severe the weaker the acid is going to be. And finally, at your equivalence point, if you're dealing with a weak acid, then the pH is going to be greater than 7. And notice the weaker the acid, the higher the pH is at the equivalence point. When we're working with titrations in the lab, unfortunately, we don't get to see these nice titration curves. Instead, what we have to do is we have to use an indicator. Now, if you notice in this figure, this is showing you, for example, the one on the left-hand side is showing you phenolphthalein. So for phenolphthalein, it's going to turn colors when the pH is between 8.3 and 10. And so what this means, if you notice, for this titration curve in the top left corner, what that's showing you is you adding a base to an acid. And so you're going to start off with a low pH, and then it's going to increase in the typical titration curve fashion. Now notice that in this case, phenolphthalein is a great indicator because the equivalence point is going to fall within that range in which the phenolphthalein is going to turn colors. And so that's a great indicator because as soon as it turns colors, you know you've hit your equivalence point. Because otherwise, there's no way for you to know when your number of moles of acid and base are equal. Since that is a good indicator, let's see what a bad indicator looks like. Methyl red indicator, it turns colors between 4.2 and 6.0 for pH. So if you notice here, if you have an acid and you're adding a base to it, that color change is going to occur way before your equivalence point is reached. And so that's going to be a bad indicator because, well, once it turns color, it's not going to turn anything else. So there's no way for you to know exactly when the equivalence point happens. Phenolphthalein in reverse, if I start off with a base and I'm adding an acid to it, phenolphthalein is going to be a terrible indicator because as you notice, the equivalence point is around 5, and that's not within the range at which phenolphthalein is going to turn color. So phenolphthalein is going to turn purple before you even reach your equivalence point, which is the whole point of doing a titration in a lab, figuring out where that equivalence point is. In contrast, methyl red would be a great indicator for this one because it turns that yellow color between 4.2 and 6 for pH. So you can add your acid to your base, and then once you've hit your equivalence point, you'll actually see that color change. Now, to reference back to terms that we talked about in the beginning of this lecture, the equivalence point is not when it turns that yellow or that purple. Instead, that's the end point. So in fact, you rarely will stop right at your equivalence point. Instead, you normally pass by the equivalence point or you're not quite there. So the endpoint is when it turns colors. So the last type of titration that we're going to be talking about is the titration of polyprotic acids. Now notice there are two equivalence points here, and the reason why there are two equivalence points is because you actually have two separate acids that are going to be reacting with the hydroxide ion. The first one is H3PO3, which is going to be losing one of its protons to become H2PO3, and once the number of moles of the H3PO3 equals the number of moles of OH, you'll hit one equivalence point, and then you'll hit a second equivalence point once the number of moles of H2PO3 equal the number of moles of OH.